As you can see here, we've got the Albatross UAV upon 3 different colliders, which are measuring the weight which is experienced on each of the landing gear. We can use this to find the total mass and to find the position of CG by changing the Z position of the CG on inside the model. This MATLAB script was used to calculate the total mass and CG, as you can see on the right. These values line up perfectly, well, close to perfect, with the values in the Unity coursework. You see here that mass is 7 kilos. As we can see here, the Albatross is being moved closer and closer to a collider, where eventually it will touch. From there we can measure the thrust value for the specific RPM that is being shown in the flight instrument on the right. Obviously when we increase thrust, when we increase RPM, the thrust will increase as well, and then that way when we plot them we can get a nice straight line and prove that the linear relationship between the two. Okay, so here is the graph, and we can see that the relationship is the thrust equals 0.27 RPM value. And the maximum here is about 27, 28, whereas the datasheet usually says about 30 newtons is the maximum for the Albatross, but this is close enough. In this test we're going to be testing which keys do what movement on the aircraft. First up, we're going to check that roll right is right arrow and roll left is left arrow. Next, we're going to see that nose up is down arrow and nose down is up arrow. Then we're going to see that your left is A and your right is D. And then flap up and flap down is F and G. For this experiment, 2 CG values were used, one at 0.0223, which is CG1, and CG2, which is 0.05. This is all in reference to the Unity position, Z position, relative to the Mac. The damping ratio for CG1 was found to be 0.019, and the damping ratio for CG2 was found to be 0.028. It appears that moving the CG further back increases the damping ratio, which means it will reach the desired angle of attack faster. The maximum change in amplitude from the steady state for CG1 was 0.914, and for CG2 it was 1.901. And it seems that moving the CG further back makes it more unstable, and as you can see, CG2 tends to overshoot more. It seemed that about the Z location of CG for 0.065, it became very difficult to control and very, very unstable, so I would not recommend moving the CG location past this point. Interestingly though, the CG values, both of them, had the same time to respond. So from the time of the initial movement of the elevator to the time that the new position settled was both equal at 90 in-game unit times. And it seemed that increasing the freeze stream had no effect on response time, because moving the CG further back increases the amplitude of the overshoot, but gives a higher damping ratio to counteract this. Here we can see an Albatross UAV doing some not perfect maneuvers using the rolling characteristics of the aircraft. From this graph we can see that by increasing the free stream velocity of the flow, this allows for a higher roll rate. We can see in the free stream equals 10 section that the roll rate was almost 2 degrees per time unit, sampled unit time. And when we increase the free stream to the cruise speed, which is 19, we get 3.27 degrees per time unit sample. The pilot of the albatross should bear in mind that the further that the CG position is moved back, the higher the absolute change in thrust line angle is. So the difference between the angle at zero thrust, alpha at zero thrust, and alpha at full max thrust. We also found that by moving the CG position really far forward, by moving it to minus 0.08, there is a very negligible change in the thrust line angle when turning it from zero thrust to full thrust. But because the CG position is so far forward, it makes it very hard to maneuver, so it's not worth putting it there. Here we have our classic CL alpha graph. We found that alpha is 9.6 degrees where the CL is max, which is about 1.1. This is our classic drag polar, CO versus CD. Obviously there's a strange bit past the 0.1 coefficient of drag area, but still roughly correct. And this is combining CL and CD to get the lift to drag ratio. We have the lift to drag ratio applied against CL, and we can see that the maximum lift to drag ratio is 13.4 at roughly 0.55 CL. Here we have our graph of CL versus CM for 3 different elevator deflections, one for 15 degrees, one for 0, and one for minus 15 degrees. We can see that the minus 15 degree trims much earlier than the other two, and then the 0 and then the 15 degrees as expected. This demonstrates how we can move about without taking off just by using the rudder. By keeping the RPMs at a low value, it keeps the albatross more stable, which will reduce in the chance of tipping over due to excessive speeds or cornering angles. By making shallow turns with the rudder, you can effectively move about the airfield. Just remember to keep the RPM low. Okay, so first we're going to take off without flaps, and that took about 27 meters per second to take off. Well, 27 speed units according to the Unity engine. Just wheels take just touch off the ground, and then we go. And then with the addition of flaps, the extra lift allows us to use a lower velocity to take off, and for this it's about 18 units. Here we have an example of trim flight at cruise, which is about 20 meters a second. Our deflection is minus 17 degrees, so 17 degrees down,